All right, I thought I would talk my way through the exam one solution in case it might benefit some people out there. So here is the posted solution. So the problem looked like this right here. Things that we wanted to take a look at were we should have focused on the joints right here. These were particular joints. Notice that this is a rolling contact. So that means that there's no slipping going on. In here, it's going to roll and it's going to slip. So it can translate and it can rotate. Right here, it can translate, but, well, it can rotate, excuse me. So like in an instant, it's rotating about this point, but it's not translating along that point. Let me put it that way. But then like right nearby, it can rotate about this point as well. So in looking at the solution right here, we count through, here's 1. I usually count the ground as 1. And so everywhere there's a ground, that's still 1, or ground is just 1 link. And then we have 2, I call this guy, this 2, that's the entire length of the thing. And then 3 is this round piece. 4 is this. 5 is the little roller here, and 6 is this piece right here. And then, so there's 6 links. Then we take a look at the joint 1, where that's a 1 degree of freedom joint. And so I decided to call them A, B, C, D, and so forth. And only mark down the ones that were a half joint, the ones that have more than 1 degree of freedom movement, as with a J2 next to them. So on A, B, C. Where did C go? Where'd you go? C. C is this? Okay, C, D, and E, and F, G, H. Okay, and of those, A has both translation and a rotation, so it's a J2. And slot right here, this has translation and it has it can pivot about this. So that's a J2. And all the rest are simple joints. There's 6 simple joints and there's 2 of these so-called half joints. And it ends up with a mobility of 1 when you put it into the equation. Going down to this guy right here, we take a look at the number of links. This is considered a link. This is the ground. 1, and then, okay, so here's 2. So I guess I probably started over here. So I had 1, 2, this slider is a joint. This is a link, excuse me. 3, this right here. 4 is this link. 5, 6, and 7. And then counting through the joints, let's see, where did I start? I just went down, started out here, and this is a slot right here that's sliding, and it can rotate, so it's a J2. This is simple joint at B, simple joint at C, simple joint at D, simple joint E and F as well, simple joint as G. H is also, this is considered a joint. And then so H and then I right here. So this is a simple joint, and it's only A that is a J2. So we ended up with a mobility of 1. So I think there's some people made variations on this. It's not as straightforward sometimes. So I was a little lenient when people decided to count, like they counted this thing as a link right in here, but then and some people decided to count joints as multiple things, but it ended up working out because of the choices they made. All right, so here was problem 2. Here's what the problem looked like. You had these lengths right here, and I made a grid that's approximately 0.2 inches. I tried my very best to make it. It was actually pretty close to being 0.2 inches, so that 5 of these squares made an inch. And then I also gave you these lengths right here, so you could have seen that they ended up to being a 2.5. There's pretty close if you were to count from these points right there to being 2.5. It's a little bit over. So when posting the solution here, what I was asking you for was to take your compass and mark from this point A, make an arc of the length of this, and then an arc for the length of down here for the length of 3. And I try to make it convenient by making them both the same length. And so we have here in this at B, we have this is going to be the open configuration, and then down here is going to be the cross. And I wanted you to label these. I went a little overboard in labeling mine. But this is the kind of things that you would want to label. You didn't have to put the angles in there. I went ahead and put them in. And I did want the transmission angles. Some people did the interior angle. Yes, it's going to be the same here. This ends up being about 40. I think actually if you calculate it out, something like 41 or something like that. And then down here, I wanted you to write out the vector loop equation and break it down into parts, into x. Here's the x parts of it, and here's the y parts of it. And we get down to 2 equations, the 2 unknowns, and we know that this is a difficult equation to solve for these 2 unknowns. And we have to have some kind of scheme, either along an arduous algebra thing like Norton does, or we could use Newton-Raphson. Is it Newton-Raphson? Yeah, no, I might be saying that wrong. Yeah, I think it's Newton-Raphson numerical technique to converge to get what those angles are, those 2 unknowns. Problem 3, what was asked, we set up 3 positions for this ball return mechanism. I really liked this. There was a bunch of other problems that I ran across that I thought would be kind of cool, but some of them the lines got really close. So I tried to pick one that I thought would be doable, and that everybody would get if you followed the procedure, would get pretty close to being the same results. Some of them can be kind of tricky. So I try to pick a better one. I try to pick a good one. Let's see. So let's see. In my solution here, I've tried to color coordinate this. So let's call this top point. We might call that A. So I made that in red. So we join those together, and then we have the line that's perpendicular and through the center of them. I did this with little PowerPoint shapes, but I also did it by hand, by the way, when I was trying the thing out. So here's where you would get for the joint right here for that. For that link. And I could, so here's the connection point, and I've also put it into the top position as dashed. That's what I asked you to do as part of the problem. And then we'll call this point B. We could in 3 different positions of B. We connect them. That's going to be in green here, and we draw a perpendicular line to from the center of both of those. And so here should be the point where they connect and make a link. And then this purple one ends up being the link right here. So if we were to take a 4-bar of the actual mechanism right here, it would be, we could start at any point right here, but I'll start this one. This long purple one, this length is the coupler. Here's the other. So both of these can be considered rockers, by the way. The coupler, and so here, and then a ground link would be right here. But we also wanted to drive it. And so we would pick a distance. I arbitrarily picked right to there. This seemed like a decent length right here to pick off of the thing. You don't want to go too close, too narrow to this right here, because it'll be a difficult amount of torque to be able to lift the thing up, right? So if this thing has any amount of mass to it, it's harder to lift it up as you get closer to the connection point. So this is, I eyeballed it and decided this is the length that I wanted right here. It turns out when I got done with this that I found mine to be non-Grashof, so I should probably, I would have to actually revisit it, but that was not part of the problem. And so we drew the arc that I arbitrarily picked, and then I chose this spot right up here. This too was another choice that I could have made. I probably should have made, and it really determines the length of the coupler, but I probably should have made the coupler like a little longer and brought the point back up here. But it was totally okay to be non-Grashof. It's just that you need to check this and then redesign it if it wasn't Grashof, because we do want to make this driver needs to be Grashof so it can make a full 360 rotation. And even actually looking at this right now, you can actually kind of see from looking at the 4-bar that's made up of this driver that doesn't look like it can make a full 360 rotation. So that's something to be aware of and looking at it. Okay, so the distance here needed to be twice the distance for right here. So this is actually from right in between here. I measured that to be like 1.2. So this crank was about 0.6. My coupler right here, this is about 1.4. And then where I had picked the rocker down here makes this 1.2, and then the ground is 2.1. I even made my links. I brought them over here to show you what the length of it is. So that was the idea in trying to graphically synthesize this piece to make a mechanism. And then lastly, I told you that I wanted you to do a free body. We were going to do the statics. So we had this problem right here. Oops, I didn't mean to do that. Let's see. I messed it all up. Okay, nice. Okay, well, no, it is going to save it, darn it. Maybe I'll just undo a bunch of stuff. And the original problem, actually, I got out of a book, didn't give us enough angles. So I gave this 20 degrees, this 60 degrees, and this 60 degrees. Turns out that 40 degrees doesn't really help you a whole lot. Just so you know, but I was trying to lay it out here so that you could work it out and it wouldn't be too painful. I messed around with this originally without looking at the solution to it, and it was quite difficult if you did have that angle and these other two angles. So here I have I've written the thing out. I think you could make out what I've done. Yes, okay. So I broke down that force that was applied right there into an X component and a Y component. And then I broke down the distances because I wanted to take the sum of the moments about A right here, because I could take advantage that I know that this part right here was a 2-force member. So I set those up that way. So I wrote it out really longhand. You probably could have taken some shortcuts in this, but I wanted you to be able to work through and see where each of the pieces came from. So here was the, I believe this is the X component. No, this is the Y component, right? Because we're taking the cosine of this. By the way, you need to go back and take a look, and you say, okay, here's the 20 degrees from, this is going to be 20 degrees from a vertical right here. You could see that would be 20 degrees right there. So it is going to be the cosine of this angle times 200. And then in the X direction is going to be sine. So here is, we're taking counterclockwise. This is going to go about A right here. So it's positive. And then we want to have this distance right to here. I had 175 times the cosine of 20, and then this little gap right here. Oh, I because I'm taking around here, I actually could have combined these two and made this 90 times the cosine of 60. But because it was easier to draw up here this way, I went ahead and kept them separate. And so this is the full moment arm from right here that's going across for this force. And then for this force, this is also going counterclockwise. So there it is, that 200 times the sine of 20 degrees. And then we want to have the full distance right here that's perpendicular to that one. So that's the 175 times sine of 20, and again, this was 30 and 60 times the sine of 60 degrees, so that could have been 90. That would have saved like a little step right here. And so that was the full moment arm right here for this part and this part. Now the reaction, well, not the reactions, but the parts for this force at B, well, I decided to call it B. BC, and let's see. Okay, so yeah, so I made sure that I took the force FBC times the cosine of 60 degrees. That's going to be this guy right here, and that's going clockwise, so he's negative, and the distance that's perpendicular to it is going to be 60 times the sine of 60. And then likewise, this guy right here is also going clockwise. So I took FBC Y right here, which is FBC sine of 60 degrees, because it's 60 degrees right in there, in between those two. And then times the distance right here in between, that's 60 times the cosine. So we get 938.7 newtons. And then if I want to find the force that it's putting on the cutting, that's this guy right here. I know this force, so I can go ahead and I can take this, go ahead and take this, the sine of 60 times it, and that's going to be the reaction force. It's really important as an engineer that you're able to find the reaction forces, and you're able to do free body diagrams. So that's it right here. I was going to do a webcam. I was going to do a little trick, but that's all right. Let me know if you have any questions about this, and I'll talk to you soon. Hopefully everybody's doing well. I hope you and your families are staying safe, and for our friends who are from other countries, I hope you guys are managing well in this difficult time. Take care of yourselves and be safe. So take care.